Have you ever stopped to think about how much of our world runs on autopilot? From the simple thermostat on your wall to the massive rockets launching into space, there's a hidden force at play, a silent intelligence that keeps everything in balance. This is the story of control systems, the invisible architects of our modern world. And believe it or not, this story doesn't start with computers or silicon chips. It begins thousands of years ago with the flow of water. Our journey starts in ancient Alexandria, around the 3rd century BCE, with a brilliant inventor named Ctesibius. He was obsessed with creating a water clock, or clepsydra, that was more accurate than anything before it. The problem with early water clocks was simple. As water drained from a container, the pressure dropped and the flow slowed down. This meant the clock would run slower as time passed. Ctesibius needed a way to maintain a constant water level. His solution was ingenious. He designed a system with a float valve. Imagine a small float in a secondary chamber. As water flowed in, the float would rise. Once it reached a certain height, it would plug the inlet, stopping the flow. As the water level dropped, the float would sink, opening the inlet again. This constant adjustment, this feedback loop, kept the water level, and thus the pressure, perfectly stable. It was the world's first man-made feedback control system. He didn't just invent a better clock, he laid the very first stone in the foundation of automation. This concept of self-regulation wasn't just for telling time. It popped up in other surprising places. Fast forward to the 17th century Netherlands. Picture windmills dotting the landscape, their giant sails spinning in the breeze. But what happens when the wind gets too strong? A powerful gust could damage the sails or the internal machinery. The Dutch devised a clever solution: the fantail. This was a smaller windmill mounted at a right angle to the main sails. If the wind direction changed, it would push against the fantail, which was connected to a gear system that would automatically rotate the entire cap of the windmill until the main sails faced directly into the wind again. It was a simple mechanical way to keep the windmill optimally and safely positioned, all without a human operator constantly making adjustments. It was a control system born out of necessity, a beautiful example of mechanical intelligence. But the real game changer, the moment when control systems truly stepped into the spotlight, was during the Industrial Revolution. And it was all thanks to steam. James Watt, a name synonymous with steam engines, faced a critical challenge in the late 1700s. His engines were powerful, but their speed was dangerously unstable. An increase in steam pressure or a decrease in the workload could cause the engine to race out of control, risking a catastrophic explosion. He needed a governor, a mechanical brain to regulate the engine's speed. His solution, the centrifugal governor, is a masterpiece of engineering elegance. Imagine 2 heavy metal balls or fly balls attached to arms and linked to the engine's output shaft. As the engine speeds up, the balls spin faster. Centrifugal force pushes them outward and upward. This upward movement is linked to the engine's steam valve. As the balls rise, they begin to close the valve, reducing the flow of steam and slowing the engine down. If the engine slows too much, the balls drop, opening the valve and letting in more steam, which speeds it up. This continuous, graceful dance of the flyballs maintained a near constant engine speed, regardless of the load. It was the heart of the Industrial Revolution, the device that made steam power reliable and safe enough to drive factories, pump water from mines, and power locomotives. The centrifugal governor became the iconic symbol of feedback control, a principle so fundamental that it would echo through the centuries. The importance of these flyballs wasn't just mechanical. It caught the attention of scientists. In 1868, the brilliant physicist James Clerk Maxwell, famous for his work on electromagnetism, wrote a paper titled On Governors. He wasn't just describing how they worked, he was trying to understand why they worked. He used differential equations to mathematically model the dynamic behavior of the governor, analyzing its stability, This was a monumental leap. For the first time, the principles of control were moving from intuitive tinkering to a rigorous mathematical science. Maxwell's paper marked the birth of control theory, the theoretical bedrock upon which all modern automation is built. He gave engineers the tools to not just build control systems, but to analyze, predict, and optimize their performance. As the 19th century gave way to the 20th, the world of control expanded dramatically. The telephone network was spreading across continents, and engineers like Hendrik Bode and Harry Nyquist at Bell Labs were tackling new, complex control problems. They were dealing with electronic amplifiers in telephone repeaters. The challenge was to boost the signal over long distances without it becoming unstable, and devolving into a loud, useless squeal. This is the same feedback squeal you hear when a microphone gets too close to a speaker. To solve this, they developed powerful new mathematical tools, like Bode plots and the Nyquist stability criterion, which allowed them to analyze the stability of feedback systems in the frequency domain. Their work wasn't just about making phone calls clearer. It laid the groundwork for designing stable, high-performance electronics, radar, and countless other technologies. Then came World War II, a period of intense technological acceleration. The demands of warfare pushed control systems to their absolute limits. Suddenly the problems were about life and death. How do you aim an anti-aircraft gun to accurately track and shoot down a fast-moving enemy plane? The solution was the servo mechanism, a sophisticated control system that used feedback to precisely control the position and velocity of the gun. Radar would detect the plane's position. A computer, in those days a mechanical analog computer, would calculate its future trajectory, and powerful motors, guided by the servo mechanism, would aim the gun. This fusion of radar, computation, and control was a huge leap forward, forming the basis for what would become known as cybernetics. This field, pioneered by Norbert Wiener, explored the parallels between control and communication in both machines and living organisms, forever changing how we think about automation and intelligence. After the war, the world entered the space race, and control systems reached for the stars. The challenge was immense. How do you guide a multi-stage rocket, a towering, unstable behemoth, into a precise orbit hundreds of miles above the Earth? How do you keep the Apollo spacecraft pointed correctly on its 250,000-mile journey to the moon? The answer was a new era of control theory, state space representation. Led by visionaries like Rudolf Kellman, this modern approach provided a far more comprehensive way to model and control complex, multivariable systems like a rocket with its engines, fuel tanks, and guidance fins. Kellman's most famous contribution, the Kellman filter, was a revolutionary algorithm that could take noisy, incomplete sensor data from gyroscopes and accelerometers and produce a remarkably accurate estimate of the system's true state, like its position and velocity. It was the secret sauce that made the Apollo guidance computer, with less processing power than a modern calculator, capable of navigating to the moon and back. The Kalman filter is still used everywhere today, in your phone's GPS, in drones, and in autonomous vehicles. And that brings us to the present day. We live in a world saturated with control systems, most of them completely invisible. The cruise control in your car, that's a classic feedback system, adjusting the throttle to maintain a constant speed. The thermostat in your home, a direct descendant of Ctesibius's water clock, turning your furnace on and off to maintain a set temperature. The hard drive in your computer uses incredibly sophisticated control systems to position the read or write head with nanometer precision over a spinning disk. Modern robotics, from the arms on an assembly line to the rovers exploring Mars, are marvels of control engineering. They use advanced feedback from cameras, sensors, and force detectors to interact with the world in precise and delicate ways. Even the economy is a massive, complex control system where central banks adjust interest rates, the input, to try and control inflation and unemployment, the outputs. And of course, there's the rise of artificial intelligence and machine learning. Techniques like reinforcement learning are essentially a form of adaptive control, where an AI learns the best actions to take through trial and error, receiving feedback in the form of rewards or penalties. This is how AI masters complex games and learns to control robotic limbs. From a simple float in an ancient clock to the algorithms guiding rovers on another planet, the story of control systems is a story of human ingenuity. It's about our relentless quest to create order out of chaos, to build systems that are stable, efficient, and intelligent. It's the invisible hand that shapes our technology, and in many ways, our lives. The next time you set your cruise control or adjust your thermostat, take a moment to appreciate the incredible journey of that simple idea, the power of feedback. Thanks for watching. If you found this journey through time fascinating, be sure to like this video and subscribe to our channel for more stories from the world of science and engineering. See you next time.